During the Dark Ages and before, there's always been a need to throw big rocks over high walls to destroy what was on the other side. A simple goal, but the ingenious ways that this goal has been accomplished over the centuries are amazing. From the simple catapult to the Roman augegar, and finally to the trebuchet, machines of war have always become more effective. First records of a trebuchet were during the 5th century BC in China, and were powered by teams of people pulling on ropes. The design of the trebuchet evolved over time until it reached the pinnacle of rock-throwing technology, the counterweight and the sling. The counterweight design was first introduced in the 12th century AD, and was phased out in the 15th century well after the introduction of gunpowder. However, since the time of the medieval crusades, trebuchets have changed quite a bit. Some modern trebuchet designs would not even be recognized as trebuchets, such as the Merlin, a trebuchet that uses the weight of the machine to fire projectiles. Despite how trebuchet designs have changed over time, there are three characteristics that make a trebuchet a trebuchet. 1. The machine is powered by gravity, usually in the form of a counterweight. 2. This force rotates the throwing arm. 3. The projectile is thrown with a sling. Although the trebuchet may seem like a simple machine taught to high school students to demonstrate basic physics, thousands of years ago, the trebuchet was cutting-edge technology.
The trebuchet that we designed is a classic trebuchet design. The throwing arm can be pulled down to the release position, allowing us to be able to position the sling rope and the projectile. Using a fence latch, we are able to launch the trebuchet by pulling a rope, allowing for a safe use of the trebuchet. On this version of the trebuchet, we have a wide square base. We changed it from a rectangular base because we found that with the added height of the wheels, the center of gravity on the trebuchet was high enough that it would fall over. And seeing that there are foot-long metal poles sticking out of it, we decided that we should fix the problem. The counterweight, what we use to propel the sling and the stone, is on the force arm of the lever, and is half as far away from the fulcrum as the sling is from the fulcrum. This causes the speed of the sling to be increased, but halves the weight the trebuchet is able to throw. The throwing arm can be pulled down to the release position as if it was 75 pounds, even though it is 150. But the result is that the distance we need to pull is doubled. This is because the distance is doubled on the throwing arm. The purpose of the sling is to increase the distance the projectile can be shot. And since our projectile only weighs 1 pound, there is not much resistance, allowing for the projectile to be thrown great distances. The weight we used is 75 pounds of dumbbells. When this was tested and aimed, we found that the 75 pounds of weight could shoot a 1 pound rock 150 feet. We then decided to double the weight of the counterweight, theoretically doubling the distance that the rock would be thrown. However, the increase in distance was only 40 feet, for a total of 190 feet. Although we predicted that the distance will be double, it did not. We believe this is because the bucket of rocks did not stay still on the arm and jerked around while falling, causing the sling to release unpredictably. Without being able to time when the rocks will leave the sling, it is difficult to adjust the release pin accordingly.
The trebuchet is actually two things, a lever and a sling. The lever is a simple machine that gives a mechanical advantage when given a fulcrum, or pivot point. It is often used to move heavy loads with less effort. There are three types of levers. A first-class lever is like a seesaw. One end will lift a load up just as far as the other end is pushed down. A second-class lever, like a wheelbarrow, the long handles of a wheelbarrow are really the long arms of a lever. A third-class lever is like a fishing pole. When the pole is given a tug, one end stays still, but the other end flips in the air, catching the fish. The trebuchet is a first-class lever. If you look at the diagram above, you see a first-class lever. The basic parts of a trebuchet include the frame or base, beam or arm, counterweight, sling, and of course, the projectile. Looking at the pictures, you should be able to see that the fulcrum, or pivot point, is the place on the base where the arm balances. The frame is the body of the trebuchet, which is used to support the beam, and the counterweight. The counterweight is a large mass that hangs on the short arm of the beam. On older models, a person would pull down on the arm to throw the projectile, and this would make the person pulling down the arm the counterweight. The sling is a sack used to hold the projectile until there is enough energy to launch it. A trebuchet is powered by either gravity, like a heavy load, or by a force that is strong enough to be able to throw the projectile, like a person pulling it back. When the sling accelerates, it creates an arc shape, actually the parabolic arc, until one end slips off of a pin. The angle at which this happens is called the release angle. Using its own momentum, the projectile continues to fly in an arc shape until falling to the ground. This is because the motion of objects under the influence of gravity are already going to make parabolas. Let's describe this in mathematical terms, with a bit of physics. We have an object being thrown and want to know its velocity, speed over distance in relation to time. We can determine the velocity using v equals gt, with a rate of g meters per second. This is called the acceleration of gravity. It uses absolute value for gravity, 9.8 meters per second squared. Let's understand the abbreviations. Velocity equals v, gravity equals g, and seconds or time equals t. The falling body is dropped. If all of this would be graphed, you would get a parabola, opening downwards, of course.
So I'm just going to put that in the dot. The joke's going to be really hot.
Oh, yes.
You're going really slow.
Just keep going till it's
Stop!
you want to f the bit up.
Fuck the bit up.
Look at there's like fire on it.
Okay, yeah, that smells
it.
bad.
Yeah!
That smells bad. Just really
hot.
bad.
Okay, again.
What are you doing?
I'm pushing in.
No, should I stop filming this?
No, just keep filming.
Keep filming.
At least the
I've
wall.
sworn a lot. That's okay, though.
We're gonna sound
I'm dubbing over all of this. That's all good.
slow music.
It's not moving at all.
I think that's good. I think it's good there, though.
It's going in. I can see it going in.
I think it's good.
It's really slow.
Let's see it.
No, you know what? There's a nut on the other side.
A knot.
A nut. Yes.
That's probably why.
Yeah.
Alright.
So I might.
You stop moving your head in front of the
break.
camera, Drew.
It's okay.
No, it's not okay if it breaks.
If I, once I get through with this point, I'm going to jump to the other side.
Let's start with the other side.
Yeah.
Now. Grab the...
You know what? I think.
Wait, okay, I have an idea.
Great. It's definitely the knot. Look how hot that starts getting.
Yeah, let's do it higher.
Good eye, Anthony.
Let's do it a little bit higher.
No, I think we're good right
You had it
there.
on backwards. That's why. Oh god, the whole thing was on backwards. Look, the vent's gonna go through right now.
I told you not to change it.
I didn't change anything. He's the one who put it on.